Hello, good evening. Let me take some time to explain this last decision-making, quantitative decision-making assignment. In this assignment, you are required to get you're required to calculate a inventory decision based on particular setting, and after you got the optimal solution from Excel Miner, then you will have to take additional step to check how robust that result is. Okay, so it's actually one big problem with two small subproblems. So the first subproblem is presented here, and the second subproblem is actually presented here. So you need to fill in required quantity here, and then you'll need to run the simulation optimization model, and then after you got the result here, and you'll need to use that result to run a robustness check here. Okay, so basically in this video I'm going to help you go over what you need to do. I'll demonstrate some of the steps you need to solve the whole problem. Hopefully I can help you this way. Okay, so here of course in your file you won't be seeing these two worksheets because these are basically like a solution. Okay, so these are provided. Retail price, cost, and salvage value is provided. So based on these three quantities, and you can basically calculate what is the underage cost when your inventory is lower than market demand. Right? In that case, I'm sorry. Yes, it's lower than market demand. In that case, the opportunity lost is actually considered as underage cost. So this is per unit underage cost. It's actually the difference between the retail price and the procurement cost. So you get the quantity here. Make sure you use a formula instead of just punching the number here, okay? So instead of just punching 32, you actually have to use a formula D2 minus D3 to get this result. And average cost means that when you have an excessive inventory level, and then in that case, what is your average cost? So this both quantity has to be in a positive number to obtain the total cost eventually in a positive number format. So the average cost is of course a difference between the salvage value and the procurement cost. Okay, so here's how I got. So this demand, you basically, this is a certain variable, therefore we need to rely on the Excel miner to feed in random number here for 1000 times, like what we did last time. So the in this case, I am asking you to use exponential distribution with a mean of 125. So that is designated, parameter here to generate the demand. But because I want demand to be an integer, therefore after you have this number right here, as you can see, I have taken additional step to make an integer, okay, round it up to make an integer. So here you will be making your inventory decision right here, and for now I just feed in 0 because eventually the Excel miner is going to help me run this result based on simulation optimization instead of me just calculating it. Okay, and then these are also calculated quantities just for convenience, right? In order to obtain the total underage cost and total average cost. So the total underage cost is basically the total number of underage quantity multiplied by the per unit underage cost, and so is this one. So you can only have one type of cost. You can't have both costs at the same time unless your demand matches with inventory level exactly. In that case, you'll have both costs as 0. But usually, because we're dealing with uncertain demand, therefore it means that you will see one type of cost or another. So both costs together will become the total cost. Okay, so the whole setting is help us to try to determine what is the optimal quantity of this guy right here to help you minimize this quantity in long run. Okay, so that is a basic setting here. Um, in this case, we are actually using simulation in and optimization. I hope you do recognize that these are originally a separate methodology, but we're here hooking these two together to make this whole process more convenient. So as I mentioned in the classroom, not many software can do that. Usually, one software package can do simulation, the other will do optimization. But in this case, we got this nice tool here can do both things together, which is very convenient. So let me help you set up the optimization part, because we have already, did the simulation part yourself. So you probably know that you have to designate as you can see from here, you have to designate a type of distribution here. So in this case, I have used exponential with a mean of 125. So just, designate this quantity right here. And this one is using roundup function. Okay, roundup function, it will help you round up the quantity in D9 cell. Basically make it integer. So that's what it is. For the convenience, it's 0 for now, but eventually this will change. And these are calculated. This is good. So make sure that you need to understand when the demand is larger than the inventory, this quantity is positive, right? So that's why I have used f function here, and this is basically flip side of this guy right here. When you have inventory that is excessive, and then this quantity becomes positive. So, and for this is our simulation output, and with this setup done, we're gonna move to next one, which is the optimization part of setup. So for optimization part of setup, as you can see from here, we need to configure three items. First one is our decision. So our decision variable here is actually the inventory decision. So you just click here, we consider it as a normal decision variable. So just click it, that's it, okay? And then we need to consider different type of constraint here. So as Excel help us solve this problem, it needs to confine the calculation result within certain range of value. We need to exclude certain range of value that make this thing look ridiculous. So what are those conditions? You basically have to specify conditions here. So for this case, I have just added two different conditions. My conditions is that this quantity has to be larger than 0. It has to be a positive number, right? So your inventory cannot be negative. The second condition is that your inventory decision here has to be an integer, just like demand is a positive integer. So how do you add it? You just click constraint, and let's go with the normal constraint. So click the third one. We want it to be greater than 0, right? Greater than 0, and that's okay. And also we want that to be a integer, right? We want that to be an integer. I think, let me see, int means integer, so you click OK. So two constraints are added. So for third step is actually the objective function. So we are actually trying to minimize this quantity, right? That is ultimate goal that we're trying to achieve in this process. So you just need to designate that as an objective. We want to minimize it, and because we are doing simulation optimization, you basically need to specify as expected. So in that case, it will try to calculate result based on expected value of all the realization from the simulation. So just click that. I think the whole setup is kind of finished. So if you click let me see, okay, if you click your model part, if you click the model part, this is simulation, right? This is simulation, it should be familiar to you. But what's added now is this guy, okay? So you see two quantities here. That's because I have done it earlier. I just did a rehearsal. That's why you're doing duplicated value here. It doesn't really matter. So my variable here is D11. This is my decision variable. The decision variable. This variable contains my decision. Okay, and then these are the conditions. It's larger than 0. It's also an integer. So these two are basically my constraints, and my objective function is this guy right here. Okay, so all the stories are here, and after we get this prepared, we can actually run our simulation. You click here, this guy right here. It should help you run a simulation. Nice welcome dialog box. Okay, and let me see what's going on. Okay. I think these duplicated value may have caused some problem. Let me go back and fix that, okay? Delete it. And by the time you do it, it should have only one value, okay? So therefore you don't have to worry too much. It's just I did it rehearsal, made duplicate value for in my side. So let's run it one more time. Optimize. Continue. Okay, I think it's running here now. Right. Basically what it says is, okay, includes uncertainty, right? That's what we're trying to do. And it is not linear in the decision variable. Yeah, I understand that. Hence, it cannot be solved by a fast stochastic programming or robust optimization method. So what we'll do here is generally slower method of simulation optimization. That is okay. I don't think it's a really complicated problem. So click next. You see, it'll take some time to solve the problem. Okay, so I think this is where you can actually see the importance of fast computing processing power. So where you have really we got this dialog box, show trial solution. Let's just click continue. Okay, let's just click continue to see if it can further optimize the current solution. Again, this is where you actually need a very fast computer processing power. When the optimization problem gets really complicated, you really need a good computer to solve the problem fastly. Okay, yeah, fast speed. So I've been unable to find a new, better member of the population with sufficient improved. So it means it has an incumbent solution, right? It looks like it has identified a solution, but what the earlier screen is basically telling us is that it could not improve this value by continuing to search different quantity of this one. So basically what it says is, hey, this result gave us the least amount of this guy right here. So, and we keep searched it for a little while. We couldn't find another solution. I guess this one is the the optimal solution in this case. So that's basically what this whole process is trying to tell you. Solver cannot improve the current solution, meaning the current solution is a good enough solution, at least from Excel miner's perspective. So 202, and like I mentioned during the class, this is really the result generated by a black box. We don't really know whether this result is accurate or no, so we need to take additional steps to do a robustness check to see whether this result will hold, okay, throughout different scenario. So in this case, you will see this setup. Okay, you have to do some calculation here to be able to run this robustness check. So if you look at my setup, I was able to replicate like 500 random number from a random number generator. So this one is actually 500 exponential random number with a mean of 125. Okay, because like earlier, I wanted my demand to be an integer number, so I rounded up to an integer. So this is what you're seeing: simulated demand, inventory level. So this is actually the result from the previous optimization. So 202. So I'm trying to use that here, okay? But I'm actually referencing from this guy right here, inventory level. So basically, before you start, you need to make sure you have this thing set up correctly, okay? So 202 is our solution provided by the optimization engine. So you put 202 here and reference all these guys as this L3 cell. Okay, so in that way, later we change something here, and these will change automatically. And underage amount, is the difference between the demand and the inventory. When demand is greater than inventory, it's going to give you that difference. When inventory is greater than the demand, that gives you the difference. Both has to be in positive format. And basically, this total cost is underage amount multiplied by underage unit cost. And this is similar calculation that will give you total cost for this one realization. Okay, so for here, you can consider that as another simulation, just because I listed 500 different realization. So in this process, we really replicated this inventory and market demand scenario for 500 times. So what you can do is you can summarize this quantity, all the total cost, to grand total cost. Okay, so what this tells you is that in long run, okay, if you repeated this inventory scenario for 500 times, maybe 500 month, hopefully year, this will be the likely result. Okay, so 500 times, you add all these total costs, it becomes this quantity right here. So then from this point, you know what to do. This is something very familiar. We've done this together. So we've done this. This is actually a data table, right? Data table under this guy right here, what if analysis. So basically, need to set up this as a data table. I tested different inventory ordering policy. So the earlier result told me that 202 is actually what the optimal solution. To test whether that result is robust or no, I listed all different type of value here. If you like, you can list from 1 all the way to 500 or something like that. But I think I just list these ranges just to take a look at it. Okay. And if you complete this data table process, right? If you complete this data table process here, and your column cell input is actually the inventory level. Okay, so this column right here will show you the different grand total costs for each ordering policy. So as you can see, currently the lowest number is with 205. Okay, it's with a 205. So our earlier optimization tells us it's 202. So there are some difference, but difference is not very large. I can guess what's the source of the difference because the random number was generated by different sources. So this random number was generated from your Excel miner. I generate a random number using different software. So that's probably the source of the difference. But because the difference is very minor, so I don't think that's really a big deal here. Okay, so that kind of tells you the whole story, right? You use a fairly advanced technique to find a answer to a fairly complicated problem, and it went through a black box process. Therefore, you don't quite know whether the result is reliable or no. So what you can do is you can take it to additional step to do a robustness check. You can think of some other ways to do robustness check. This is one way we can do robustness check. Okay, so if you like this problem, I think you can experiment with a different type of demand pattern. You can try with a normal distribution, but in case of normal distribution, we have very clear analytic solution available using News vendor model. You can cross-check whether this will give you the analytic solution result. You can check whether both results are the same or no. This is basically what I hope you can achieve through this problem set. Okay, so I think these two are not overly complicated, but I think this gives you very, very good opportunity to engage into in-depth learning with Excel. So the the one thing I emphasized throughout the semester is actually the notion of using Excel as a modeling tool, rather than a journal keeping tool. Okay, so this problem, really represents the view of using Excel as a modeling tool wonderfully. Okay, I hope you enjoyed the study in this semester, that decision-making module, quantitative decision-making module. So a lot of cases, all these parameters generated using the quantitative decision-making process will help you, design contract, will help you guide your operation, will help you guide your strategic decision. Okay, so that's why this quantitative decision making is very, very crucial in this strategic sourcing process. I hope you enjoyed it. I personally enjoyed a lot with interaction with you guys. So I hope you have another opportunity to work with you guys in some other settings. Okay, wish you the best. I'll keep update you with some review questions for the final exam. For today, I think this is it. Thank you.